Okie doke, folks. We are going to get started with our first lesson of pre-calculus, which is hopefully mostly review. I have posted this graphic organizer that you can use to organize your notes on Canvas. If you'd like to use it, you can also just use your own sheet of paper. But we're going to do one example from each of these types and then one more challenge that you'll see in pre-calc. So we'll start with greatest common factor. This is a factor is an ingredient in a multiplication recipe. So 9 and a to the fourth in this example are factors. A squared and b squared are factors. Terms are added together. So 9a to the fourth is a term. A squared times b squared is a term, right? So when we want to analyze a greatest common factor, we want to find the most things that appear in all the terms. So this expression has two terms, and I know that a to the fourth is the combination of a squared times a squared, right? So that makes this greatest common factor just a little bit more obvious because we have an a squared in the first term and an a squared in the second term. So we can factor out an a squared and undo that distributive property, leaving behind 9a squared minus b squared. And really what we're doing there is division. We are dividing each term by something and multiplying by it on the outside to keep the expression equal. Okay, so that's the greatest common factor. Beyond that, this could even factor down a little bit further using a structure we call difference of squares, because 9 is a perfect square, a squared is a perfect square, and b squared is a perfect square. So let's talk about perfect squares, difference of perfect squares. When you have the difference, meaning subtraction, between two terms that are built completely out of perfect squares, then you will be able to factor using this pattern. The square root of the first term plus the square root of the second term times the square root of the first term minus the square root of the second term, right? So in this first example, just like the example before, we do not have all perfect squares right now. 3 and 75 are not perfect squares. However, we do have a greatest common factor. So reinforcing the last type, let's factor out a 3 and see, oh, now I do have a difference of perfect squares. N squared is a perfect square, and 25 is a perfect square. 25 is 5 squared. So now I can see who's A and who's B. N is A and 5 is B. So this will follow n plus 5, n minus 5. Now that we've looked at that structure, we can go back a slide and finish this process because we have 9a squared minus b squared. That is 3a all squared. Remember, this 2 was not acting on this 9 because parentheses did not invite it to the party. Now I've used parentheses to invite this 2 to act on this 3. So 3 squared is 9, a squared is a squared, and we have the first perfect square. Minus b squared is just that. So if we want to factor this, we have our GCF out front, and then we say 3a plus b and 3a minus b. So there's a little bit more fun of a greatest common factor with a difference of squares. All right, moving on to sum and difference of cubes. This one may be new, but it does follow the same pattern. And let's see, this is a little bit messy, so let's fix this. The sum a cubed plus b cubed equals a plus b and I'm fixing our formula, but we'll make it happen. All right, so the signs will always follow a pattern. For a cubed plus b cubed, the sum of cubes, we have a plus b times a squared minus a times b plus b squared. That is, we'll always have a binomial, a 2-term, and a trinomial, a 3-term set of factors. And the signs will go same, opposite, and always positive. Same, opposite, always positive. And that follows for the difference formula. Same, opposite, and then always positive. So remember, soap, same, opposite, always positive. So for this first example, 27 and a 125 are perfect cubes. 3 cubed is 27, and 5 cubed is 125. 5 times 5 is 25, and 25 times 5 is 125. 3 times 3 is 9, and 9 times 3 is 27. So what we're looking at here is we're looking at 3 cubed minus 5m all cubed. Now we have it in this format. Something cubed minus something cubed. So we can take those somethings. The a is the 3 and the b is the 5m, and follow the pattern. We have 3 minus, because it's the same sign, 5n, times 3 squared, opposite sign, 3 times 5m, always positive, 5m squared. And we can simplify that trinomial and raise those terms to powers. So 3 squared is 9, 3 times 5 is 15, and 5 squared is 25. So here is our factored form, and it turns out that trinomial on the end, that quadratic, will never be factorable. So you're always done when you reach a sum or difference of cubes. All right, moving on to the next example. This is our most familiar type of factoring, right? This is our trinomial factoring, quadratic type. When a is 1, we're really just saying what multiplies to c adds to b, and that's referring to our ax squared plus bx plus c standard simplified form. So if I want to come up with that, there's lots of different ways that people do this. I like to use the X puzzle with what it needs to multiply to on top and add to on the bottom. But whatever quick way you've learned to factor, you can use yours as long as it's consistent and gets the job done. If I want things to multiply to 40 and add to 13, I'm going to start by making a list of factors of 40. You could say 1 in itself. You could say 2 and 20. You could say, and if you start having trouble coming up with this list of pairs, you can also make a factor tree and say, hey, I can break down every number until it reaches the product of prime factors, right? So 40 has a prime factorization of 2 times 2 times 2 times 5. So I know 2 times 2 is going to be 1, and if I use 2 and 2, I have to use 2 and 5 as well, so 4 and 10 makes 1. None of these in my list add to 13 yet, so I have to keep going. I also know that I could do 5 in this list times 8. Hey, 5 and 8 add to 13, so I have finished. There it is. So that's what we're going to split our factors into, x plus 5 and x plus 8. I double checked the signs that everything's going to work out nicely, and it does. Now, when a is not 1, we're using this same process, except we amend it just a little bit. And this actually works for the simpler version, so it's better to memorize this version. Multiplies to a times c and adds to b. So now we want something that multiplies to 7 times 28 and adds to 53. Oh my goodness. Well, we're not immune to doing just a little bit of arithmetic. 7 times 8. Think to yourself for a moment. And I'm kind of one of those people that sometimes forgets a few multiplication tables, but you can always work your way backwards, right? I know 7 times 7 is 49, so 7 times 8 will be 7 more than that, so 56. And 7 times 2 is 14. 14 plus 5 will be 19. 196. So I need something that multiplies to 196 and adds to 53. Yes, this is a little bit heavier lifting than I'll make you do without a calculator, but I do want to remind you of how we need to use our brain for a little bit of arithmetic occasionally. All right, so if we want something that multiplies to 196 and adds to 53, 196, we already know that two factors are 7 and 28. Check those, right? We can also make a factor tree for 196. 7 and 28 get us started, and then 28 is 4 times 7. So the prime factorization of 196 is not terribly complicated. It's 7 times 7 times 2 times 2. So there's not a ton of combinations to check here. So we could do 2 times 7 times 7 is 49 times 2. We could also do 4 times 49. Hey, 4 times 49 is going to get it there, right? That's 53. So I can stop there when I find it. And then when we're doing factoring where a is not 1, this first coefficient is not 1, we can't just use those two numbers in our two linear factors. This would not be correct. A plus 49. This is not correct. And I want to do that in red. Because a times a makes a squared, not 7a, right? So the correct way to go about it is to take the middle term, 53a, and split it into 49a plus 4a. These two numbers come from these two factors. So we're playing the same game, but we're using the results differently. Now what we're going to do is we're going to factor by grouping. And I don't love doing parentheses around what I'm grouping, quote unquote grouping, because it makes your brain frequently turn it into multiplication. And that's not what's happening. But from each of these groups, we're going to pull out a greatest common factor. So 7a squared plus 49a has a greatest common factor of 7a, leaving behind a plus 7. The second set of terms, I have 4a plus 28. That has a greatest common factor of 4, leaving behind an a plus 7. Now I see between these two terms, because we have 7a times a plus 7, that's a term, and 4 times a plus 7, that's a term, we have common factors, right? 7a and a plus 7 are all factors in the first term. 4 and a plus 7 are factors in the second term. They both have a plus 7. That's what we call a common factor. So we can factor it out, leaving behind 7a plus 4. And there is our fully factored form. It does not matter which factor you list first, whether it's a plus 7 or 7a plus 4, because multiplication is commutative. So we can scoot it around and do it in a different order. A times b is the same as b times a. Alrighty. That brings us to our next example, which is grouping, which is exactly the same thing we just did, but we don't have to do the first splitting the middle term, right? Here we had to split the middle term and then factor by grouping. This is how we handle 4-term polynomials. Now, there are definitely 4-term polynomials that are not factorable by grouping, but many of them are. So let's try the process here. And really, it makes our lives easier because we don't have to come up with the split of the middle term. We just get to start grouping. So the first two terms have a common factor of 4x squared, leaving behind an x and a 7. The second two terms have a common factor. Now here's the tricky part. You have to decide whether to factor out the negative or leave it inside. Because our ultimate goal is to create this common factor situation, we want what's to be left to match this binomial term, factor in the first term, right? So we want what's left over to be positive, meaning what I have is negative. I need to factor out the negative. So I'm going to factor out the negative, and the GCF here is 9. Now, if I factor out a negative, positive 63 divided by negative 9 will be negative 7. So just be really careful with those signs. Now I have created my situation where I have a greatest common factor. We'll factor it out and leave behind 4x squared minus 9. And if you are thinking you're ready to move on, take a second and see what you notice, because we're not done. I hope you noticed a difference of squares. So we have 2x squared minus 3 squared. And no, you don't have to show that step every time. However, I like to remind me, what am I actually using in my difference of squares pattern? So I should have 2x plus 3 and 2x minus 3. This is my fully factored form. All right. Last but not least, I want to talk about quadratic structure, because College Board is not going to make you do a difference of squares or a sum of, or they will make you do difference of squares. What I mean to say is difference of cubes or sum of cubes. While that is not on your AP exam, it may be on my tests and your homework. But this is one of the big ones that College Board uses and makes you recognize. You know how to factor quadratics, right? So in this first example, if we want something that multiplies to 3 times negative 5 and adds to negative 2, we could say 5 and 3, where the 5 is negative, right? And we could split negative 2 into negative 5x and positive 3x. And order doesn't matter, but it actually is a little bit prettier if I do it the other way. So I'm gonna do that, minus 5. And we could factor this by grouping as 3x leaves behind an x plus 1, and negative 5 leaves behind an x plus 1. This is 3x minus 5 times x plus 1 is our factored form, right? Okay. What if instead of using x for our variable, we substitute in a whole expression? And my image has moved, so this is a little bit funky as it's transferred in. But how about we just make it easy and cover these up and start fresh. And I'll just write them out because that'll make it nicer. So if we have a quadratic, the same quadratic in terms of x minus 1, that says everywhere there's an x, I'm going to use an x minus 1. X minus 1, x was squared, so I'm squaring x minus 1. X wasn't squared, so I won't square this one. There we go. Now, everywhere there was an x, there is now an x minus 1. This is going to be really similar to a process we call composition that we talk about in a few days. Now, this structure can be factored the exact same way, right? Everywhere this factored form has an x, it will have an x minus 1, right? So we could write the factored form of this as 3 times x minus 1 minus 5 times x minus 1 plus 1, which does simplify, right? But you could come up with that factored form by substituting a variable and factoring it and seeing that happen. So let's do another one. The natural log is, what's this supposed to say? The natural log is ln of x. ln of x. So if we substitute in natural log, this is, and I'm going to do it in another color, we have 3 times natural log of x, and the whole natural log of x gets squared, so I use parentheses, minus 2 times the natural log of x minus 5. Now, remember, if we use a variable, I'll use u to set equal to the natural log. We can say this is 3 times u squared minus 2u minus 5, right? This factors to 3u minus 5u, minus 5 times u plus 1. If we said u is equal to the natural log, we can replace the u in here with our natural log of x. Okay? So you can see the connection between our original standard form and our original factored form. And if you see this quadratic type, right, we need to be able to recognize, hey, do I see the same function raised to the second power, raised to the first, raised to the 0? Do I see descending powers? Can I use quadratic form to factor that? All right. This is obviously was not on your graphic organizer, so I hope you added it to the back of that sheet if you chose to print it out or just continued writing. And if you choose to transfer over to the graphic organizer, I have a hard copy printed for you. You can get when we get back to school. Totally up to you. But that concludes our factoring lecture. I hope to see you tomorrow. Stay warm in the snow.